Hey guys, bummed that we're not in person today, but we'll go and get through the second lesson here and get back to what we kind of finished talking about last week. I don't know if you remember. If you look back over your notes, you'll see that we mentioned the idea of binary numbers last week. So we talked about the fact that we use a base 10 number system, right? We've got 10 digits on our hands. Makes sense that we would count things in that fashion, that we would have 10 digits 0 through 9 in the base 10 system or the decimal system, as you might call it. But we say computers, they don't think that way, right? Computers only have two numbers to deal with. We can represent those by a 0 and 1. You can think of it as off and on. You can think of it as false and true. Those are just all ways to think the way a computer thinks at its in its simplest form, right? It's electricity running through a circuit. And so for computers, either there is electricity or there's not. It's either on or off. And so, like I said, in binary, which is the number system that computers think in, we consider that to be in thinking in zeros and ones. Like I said, off or on would be another way to think about it, or false and true, right? And so what I want to talk about today, what I want to begin with is understanding binary numbers and understanding how we can take a binary number and convert it to a decimal number, which is what we've been learning to work with since we were little kids, right? So how would we go about doing that? Well, the first thing we need to refresh ourselves in is the way that our base 10 number system actually works, right? So if I had a number, let's say 241. Now we know that this is the ones place, right? That's the ones place. This right here would be the tens place. And this would be the hundreds place, right? If we added another one, it would be the thousands place. And what may not be immediately obvious to us, but we should understand, is that each of these numbers here are powers of 10, right? If I raise 10 to the 0 power, what do I get? I get 1. If I raise 10 to the first power, I get 10. If I raise 10 to the second power, I get 100, right? And so this number, the way that we understand this number is in our decimal system, is that this is the same as 100, since this is the 100ths place here on the front. 100 times 2 plus 10, since that's the tens place, times 4 plus 1, since that's the ones place, times 1, right? And if we add all that up, what do we get? 200 plus 40 plus 1, or 241, right? Which was our initial number. Well, that's exactly the process that we're going to use to convert from a binary number to a decimal number. Okay, so let's just take a simple example here. A binary number would look something like this: 1 0 0 1, right? It can only use ones and zeros. So when we think about how it works in our decimal system, it's the same way in the binary system. Instead of being powers of 10, it's going to be powers of 2, right? And so this here is going to be the 2 to the 0 place, or another way to think about that is, is that's a 1. This right here, so that was the first one. This one here is going to be the 2 to the 1 place, or the corresponding decimal value would be 2. This is the 2 to the second power, or 2 squared, which is going to be 4. And then this is 2 to the third power, and 2 to the third power is 8, right? So if we do this just like we did with the number 241 just a second ago, the way that we would convert this to decimal form is we would say 1 times 8, right? Because that first one is in the 8's place, plus 0 times 4, since it's in the 4's place, or the 2 to the second place, then 0 times 2, and then finally 1 times 1. So when we add all that up, 8 plus the zeros go away, 8 plus 1 is just going to equal 9, right? So this number, so 1001 in binary form represents 9 in decimal form, okay? Let's do one that's a little more difficult. Let's try 1 0, 1, 1, 0, 1, 0. And this time, instead of writing 2 to the whatever power, we're just going to go ahead and do the multiplication on that, do the raise it to the power, and say, since this is 2 to the 0 power, then this is going to represent 1, this is going to represent 2, 4, 8, 16, 32, and 64. So it doubles each time, which again should make sense to us because these are all powers of 2, right? So what does this equal in decimal form? Well, it's going to be, this time we're going to ignore the spaces that have zeros because they're not going to contribute to the final number. And since all the spaces that have ones are just going to correspond to the numbers that are below here, we're going to have a 64, right? Plus a 16, plus an 8, plus a 2, right? So 64 plus 16 plus 8 plus 2. And when we add all that up, punch it in our calculator, whatever, we're going to get the number 90, right? So that's what this binary number would be in decimal form. It would be 90. So be sure that if I give you that on a quiz or a test that you know how to do that conversion, okay? One of the biggest reasons that I wanted to make sure that you understood this is because I didn't want you guys to be lost. If you ever see some nerd wearing a t-shirt that says something like this, right? Let's see. All right. There are 10 types of people in the world, those who understand binary and those who don't. Now, a person that doesn't understand binary, they would have read that statement like that, but that's not how you would read that statement now that you understand binary, right? Because you would recognize that 1 and 0 is a binary number, and this is the ones place and this is the two place. And so in decimal form, 1, 0 is actually the decimal number 2, right? Whoops, the way we did it before was 1 times 2, right, equals 2. So there are two types of people in the world, those who understand binary and those who don't. Pretty funny. Probably none of you are going to run out and buy a shirt like that, but you might. I think it's actually kind of cool, right? All right, let's talk about going the opposite direction. So we talked about going from binary to decimal. What if we have a decimal number and we want to go to binary? So the process is just the reverse of what we did before. We'll do a simple one, 23. So what we're going to do is we're just going to what we're going to have to do is we're going to put some spaces here that kind of represent the different places in our binary number. And we'll just say this is the ones place, the 2, 4, the 8, the 16, the 32, and the 64, right? So what you want to do is you want to start with the biggest number that is still smaller than the 23, right? And so when we look at these numbers here, the first one that's going to be like this is the 16. So you want to put a 1 there, all right? Because that way we have 16 first, and then we're going to have to add something to 16 that's still going to be less than or equal to 23. So 16 plus 8 is going to put us at 24. So we know that's not going to be there. For 4, 16 plus 4 is going to give us 20. So we can put a 1 there, and we're going to add a 4 to our number over here. We're still 3 away from 23. So what are we going to do? We're going to put a 1 here. That'll give us a 2. And then we'll put another 1 here, which is going to give us a 1. And so when we add all that up, we get the decimal number 23. So the binary form of 23, we could have put zeros here to pad it. But, you know, just like we would do in with our decimal numbers, we don't usually write 23 as 0023. Which is true, right? It's still the same number, but we don't usually pad it with those zeros on the front. And so 23 converted to binary, the answer would be 10111. Okay. All right. So let's move on to another common number system that you find when you're using computers. Binary. Maybe arguably the most common, but this one's also very common as well. So let's talk next about hexadecimal. Hexadecimal numbers. All right. So where binary has 2, remember, like bicycle, bicycle has 2 tires, 0 and 1, two numerals, 2 digits. Hexadecimal has 16 numerals. All right. Well, you should immediately say, I'm gonna have a problem with representing that, right? Because I don't have 16 numbers to work with in my decimal system to think about that, right? We only have 0 through 9. That's the only numbers that we have. So what they do in the hexadecimal world is that they use 0 through 9, but then they add to that the first 6 letters of the alphabet, right? So 0 through 9 will give us 10 numbers, and then A, B, C, D, E, F will give us an additional 6 digits, characters that we can use to represent a hexadecimal number. Okay, so this is 16 numbers, so you could call it hexadecimal, or you could call it base 16, just like you could call binary base 2, just like you could call decimal base 10. And the way that this looks, let's see. Let me just share real quick my notes. Where is that? So you can see it. Here's kind of a chart that's in the book. You can look at this in the book. This is on page 32 in the book. In the book, you'll see a chart that looks similar to this, right? So they give you the decimal column over here. So these are the numbers 0 through 15 in decimal, and in hexadecimal it goes 0. Like I said, 0 through 9 would all be the same in hexadecimal as they are in decimal. But then when you get to the number 10 in the decimal system, that would correspond to A over here in the hexadecimal system. And so 11 would be B, 12 C, 13 D, 14 E, and 15 F. And of course, we already know how to take these decimal numbers here and convert them to binary. We just learned how to do that. So here's the corresponding binary numbers to the corresponding hexadecimal numbers. Okay. And so as you see in my notes here, each character represents half a byte. So when you see a hexadecimal number, it's half a byte. We learned last week that a byte is 8 bits, right? So let me go back to our, there we go, back to our whiteboard. A byte is 8 bits. So if each character in a hexadecimal number represents half a byte, then it would be 4 bits. Each character represents half a byte, or 4 bits, or here's another vocabulary term for us, or a nibble. Right, so we got a byte, which is 8 bits, and if you don't take a whole byte, you just take a nibble. But just like they did with byte, they stuck a Y in there for byte to represent 8 bits, right? This is how you spell byte, and you spell nibble with a Y instead of an I, like when we think about eating food. All right, so if one character represents 2 bytes, then you're going to use 2 characters to represent an entire byte. And this is kind of an important number system when we start defining color digitally. So listen, we need to understand a little bit about converting between the hexadecimal system and converting to decimal numbers or binary numbers. Okay, so let's just take a quick example of that. Let's say we have this hexadecimal number, D2E. So what would that be if we want to convert it to binary? Well, what we could do is we could look at the chart that we just saw, and if we were to look at the chart on page 32, we would see that D in binary equals 1101. We would see that the number 2 equals 0010, and we would see that E equals 1110. Okay, and so if we were to write that out in binary, we would just write it like this: 1101. Often you kind of group them in groups of 4, just so it's a little easier to read. So we would just write them all out like this: 1, 0, 1, 1. And then we can convert that to decimal as well. Again, we could look at the chart and we could do it that way. But we know how to convert. Well, actually, though, the chart's not going to help us as far as the big number, right? So if we were going to convert this to decimal, we'd have to recognize again that this was the ones place, and this was the 2, and this was the 4, and so forth. Do the math with that. Like I said, this is common in the when we start representing colors digitally. For example, FF in binary, right? If you look at the chart, it's 1, 1, 1, 1, but in decimal, it's 255. Okay, and so usually whenever you're dealing with some sort of software for editing photographs or creating digital images, when you choose colors from your color palette, you have the option to enter that color in as in its hexadecimal form. So you could enter FF, or you could use the decimal representation of the hexadecimal number and enter 255. All right, so we're going to look at some of that in the next chapter, and we'll see that. Just want to quickly mention octal numbers. Not going to do as much with those, but again, the concept is exactly the same, right? Octal numbers use the first 8 numbers of our decimal system, and so it just includes 0 through 7. This is a base 8, right? It's a base 8 number system, and so we can figure out easily how to convert. If we have 174, right? We know this is going to be 8 to the 0. This is going to be 8 to the 1. This is going to be 8 squared. And so 174 then would correspond to 174. We'll just write down below it here. 8 to the 0 is 1. 8 to the 1 is 8. And 8 to the second power, 8 squared, is going to be 64. And so how do we convert that to decimals? To decimal? We would say that it's going to be 1 times 64, right? Plus 7 times 8, plus 4 times 1. So when we punch that in our calculator, we get 114, right? So the conversion process when we're going to decimal works exactly the same for all of these. It's just for hexadecimal, when we looked at that, we're going to have to convert that one because we don't have enough numbers to represent the 16 characters in hexadecimal. We're going to convert it first to binary using a table like the one that we have in the book, and then we can go from binary to decimal. Okay. All right. Let's move on to our next topic, which is Boolean logic. And Boolean logic, it has to do with it's a branch of algebra that has to do with doing mathematical operations on when you've only got 2 values, right? When you've just got zeros and ones, like computers think. So if we have a 0 and a 1, or a true and a false, you know, there's some mathematical operations that we can do on those as we use Boolean logic. And there's 4 operators. 4 operators in Boolean logic. When I talk about operators, I mean like when we're doing basic math in the decimal system, the operators we use are the plus and the minus and times and divided by. And those are all operators that we use. Well, in Boolean logic, kind of the 4 basic operators that we're going to deal with are and, or, not, and then finally XOR. All right. And depending on what programming language you're using, there are different ways that these are represented in the various programming languages. So we're just going to leave them for now, just as the capitalized words. You'll when you're reading the section in the book, he's got some of the examples of ways that these might be represented. but just for simplicity's sake, and so that we don't get confused, we're going to talk about all of them and just use the capital word form of it. All right, so let's go through each of these operators. Make sure that you recognize that there are 4 operators that we're going to focus on and understand what each of those means. So let's talk first about and, the and operator. How does that work? Well, the basic definition of and is that both sides must be true to get a true. What do I mean by that? Well, what I mean is that if you and a true with an and, with another true, then in that case, you will get a true. All right. Remember what I said, the computer's thinking zeros and ones, and that could be thought of as false and true, right? And so we could rewrite this 1 and 1 equals 1, because both of those are true. But if we have anything else besides 2 ones, the answer is always going to be false. So a false and a true, right? Because they're not both true, a false and a true is going to be false. Writing that in zeros and ones, that means 0 ANDed with a 1 is going to be 0. Okay. And of course, if we reverse that, 1 ANDed with a 0 is also going to be 0, and 0 ANDed with a 0 is going to be 0, because there are no trues, because we don't have trues on both sides. We don't have ones on both sides. So it's always going to be a 0 or false unless both of them are 1 or true. Okay, so that's the way and works. Let's talk about the next one. Or is kind of, I kind of think of that as sort of the converse of and, whereas with and, both have to be true to get a true. With or, only one has to be true to be true. And so why do I think of that as sort of the converse or the inverse or the opposite of the and? Well, it's because must have 2 zeros to get 0. All right. Just like before, you had to have 2 trues or 2 ones to get a true or to get a 1. Now with an or, you got to have 2 falses to get a false, or 2 zeros to get a 0. All right. So if we had, like we had before, true or true, when you do that mathematical operation using Boolean logic, true or true is going to give you a true, because all we need is one of those guys to be true, right? So 1 or 1 equals 1. And so if we had a false thrown in there, it wouldn't matter. As long as one of them are true, we can still get a true. All right. That's 0 or 1 equals 1. So if I reverse that, 1 or 0 also equals a 1, because one of them's a 1. And the only case where you get a false or a 0 is when you're ORing two zeros or 2 falses together, right? 0 or 0 equals 0. All right, so and this sort of makes sense, right, when we think about it in the English language. When I say something and something, I'm including both of those things. And so that's why you got to have 2 trues for you to get a true. Both of those things have to be true in order for the final result to be true. But when we say or, right, you can either take, just because I'm looking at it on my desk here, you can either take the lamp or the globe. Well, you could show up with either a lamp or you could show up with a globe. It would have been a positive outcome of the statement that I made if you showed up with either one of those. And so in the case of or, if any side is true, and both could be true, but if either side is true, then you're going to end up with a true, right? You just need one of them to be true. What about not? Not, again, like we think about it in English, when we talk about not something, we just mean the opposite of that thing, right? So it's so with a not, you simply reverse the expression. Okay. So as an example here, if you do a if you not a false, then what is the reverse of a false? Well, it's a true. So the not operator on a false value is going to give you a true value, right? So thinking about that with we could rewrite that using ones and zeros as not 0 would equal 1, right? Or not 1 would be the opposite of 1, which is 0. You can nest operations too, just like you do in the math that you've learned previously, right? If I do not 0 or 1, just like in the order of operation, just like you've learned it in algebra, would be, you know, anything that's in parentheses, you do that first, right? And so we would do the 0 or 1 first, and so we're going to not. What's the result of 0 or 1? Well, remember the or statement. If either side is a 1, then the outcome is a 1. So this is the value of what's in the parentheses here is 0 or 1 equals 1. So now when we not that 1, we take the opposite of it, then our final answer is going to be 0. Okay. And then there's one last operator we wanted to talk about, and that was the XOR operator. And so the XOR operator, the definition of that is that one, this is important here, one and only one, all right? One and only one side of the expression must be true. In order for the entire and for the entire expression to be true, right? So one and only one can be true. So, you know, before we saw that a true and a true equals true because both were true. We saw that true or a true was true because either of them could be true, either or could be true in order for it to be true. But in the case of the XOR, a true XOR, a true, that equals false. Because again, one and only one of them can be true. We would have to have a true on only one side, like true XOR false. Then that would equal the true, right? Or to kind of reverse it, 0 XOR 1, that would equal true. All right. So hopefully that makes sense to you. And if it doesn't, maybe reading through it in the book after you've seen the lecture will kind of help it click a little bit better. We want to talk about one final topic, which is the topic of logic gates. Okay, and so logic gates, a logic gate is a physical device. A logic, by definition, a physical device that carries out a logical operation. A physical device that carries out a logical operation. So this physical device receives ones and zeros, right? Electricity is run through it. Either there's the circuit is closed, so the electricity flows, or the circuit's open, electricity doesn't. And these electrical impulses are put into this physical device, and then it will output a particular signal on the other end. So basically, you have a 0 and a 1 that goes into a logic gate. If I were just to sort of represent that as as a circle here. You got a 0, you got zeros and ones going in, right? Could be a 0 and 1, could be a 1 and a 1, some kind of signal coming in, and then you've got a single signal coming out. So depending on what the purpose of that logic gate was, you'd either get a 1 or a 0 coming out the other side. Okay, so it's a physical device that does that. But in order for us to think about logic gates, we're going to use the process of abstraction, because it's talking about the details of how you would physically build such a circuit. That's beyond the scope of this course. And so we're going to use abstraction to talk about it. And it's important that you understand what abstraction is, because we do this kind of thing in computing all the time. So abstraction is the process of reducing information, the process of reducing information and detail to focus on relevant concepts. All right, so we're having to correct an error in my notes here. So the process of reducing information in detail to focus on relevant concepts, right? We don't want to get it bogged down in all the details of how that physical circuit works, because frankly, for our purposes, we don't care. Someone else is doing that, right? I told you guys I had an electrical engineering degree, so we found out about the details of how that works internally, but I've forgotten all that now. So what we're going to do, we're going to abstract it out, and we're going to just draw some pictures here that represent these logic gates. And these logic gates are going to correspond to the 4 operators that we just learned. Okay, so we're going to use abstraction to talk about logic gates. And these are the symbols that we're going to use for it. So, you know, one of the things that we said was and. So an and signal, an and gate is going to look like this, right? 2 inputs, just like we were anding things together, true and false, or 0 and 1. And then you get some value that comes out. The OR gate is going to look like this, right? The signal coming out, so that's the OR. The NOT is going to look like this, and you may recognize some of these things if you've ever seen some electrical drawings or whatever. You know, some of this may look familiar, electrical circuits. And then the XOR is we're gonna draw it like this. It's gonna sort of be like the OR, but have that extra line on there. Okay, so this is XOR. And so when we we're gonna do some problems where I give you a diagram, right, that includes these logic gates, these and, or, not, and XOR gates, and then have you write down what we call a truth table based on that particular drawing, right? So let's do an example of that. So these are truth tables. Again, because we know we're talking about, we have that term because we use the value 0s and 1, we talk about, or 1 and 0, true and false, right? So truth tables, is the outcome going to be true or false? So let's just have a simple one here, for example, where we're going to draw an XOR gate, right, that looks like this. And let's see, it's not quite all the way down here. There we go, and then we'll come out there. These are our 2 inputs, and so here we're going to have an A and a B input, and we're going to call the output R. We're just going to use that variable to stand for a result. And so in this particular one, R equals A XOR B, right? Because that's what that drawing represents. And so let's draw the truth table. And the truth table basically gives you all the possibilities for these A and B inputs and the possible value of R that results in that. So I'm just going to draw a little simpler here. Well, we'll go ahead and do it like a full grid, just so it'll. It's probably a simpler way to do this I think I need one more, right? 1, 2, yep, one more. Probably a simpler way to do this in Zoom, but I don't know what it is. So I probably could have included a picture. But you know what? You're going to have to be drawing this down, writing this down as I'm doing it. So I might as well write it down too, right? So up top here, we're going to have columns that represent the values of A, B, and R, okay? And so we'll just start with, what if we have a false for A and a false for B? Okay, and all the possibilities are going to be represented like this. So false, false, we could have a false true. We could have a, whoops, a true false, or we could have a true true, right? Those are the only possible inputs that we have. Those are the only values that A and B could represent. And so for each of these, when we consider it, we remember what XOR means. It's only true when one and only one of the input values are true. So the only times that would be the case would be on this line here, right? Only one of the inputs is true, and on this one here, only one of the inputs are true. So both of the other ones are going to be false. So that would be our truth table for that particular diagram, right? We could have done this as zeros and ones, and actually I kind of prefer the 0 and 1 option. It's just a little easier to deal with, less space on the paper, right? So if I just kind of do that real quick, if I were to rewrite it using zeros and ones, it takes up a lot less room. A, B, and then R, and so we have 0, 0 as our input, 0, 1 as an input, 1, 0 as an input, and 1, 1 as an input. And so the corresponding values here would be 0, 1, 1, and 0. Right, so that's the result as both of those inputs go in. Okay, so I'm not going to do the last one, but I'm just going to show it to you. This kind of last problem that you could do a truth table for. And so I might give you a diagram that looks like this, right? So we have AB right here. All right, and then and so this is an AND gate. We should recognize that symbol, and we're going to go from the AND gate into an OR gate, and we got a C input right here, and then from that we would go into a NOT, and our final output would be R. So suppose I gave you a diagram like this, and I said, give me a truth table for this. So let's write down what if we were to write it down not using the symbols, and just write it down like we learned a minute ago, just using the words, what this would mean is that R equals, and you have to kind of go backwards. So R equals not, right? That's what this symbol here represents, not. And we'll put everything in parentheses that we're knotting here. Not, and now you're going to have to sort of think through what we've got in the front here. And that is, we've got an A and A and B operation that has to take place. And then whatever the outcome is of the A and B has got to be ORed with this C that's going in. Let me grab my eraser here just so we can see what we're talking about. So the A and B operation that happens here, whatever the outcome is of that, has got to be ORed together in this operation with C. So we're going to OR that with C, and then we're going to close our outer parentheses, and then the whole thing, we're going to knot that. Okay, so I'm not going to do the entire table, but we'll just walk through a couple of options here. Obviously up top, you're going to have do some columns here. We'll need A, B, C, or. Yep, that's all we need. So A, B, C, those are our inputs, and then R is going to be our final output, right? And so we'll just do a few lines here and see what the answer would be for those. There's 3 inputs. And so we're going to have a total of 8 possible results there. Should make sense because 2 to the third power is 8, right? And so we're going to start with 0, 0, 0, right? And then from there, we're going to go 0, 0, 1. And then from there, we're going to go 0, 1, 0. And then we're going to do 0, 1, 1. And then the next one in that order would be, my next row would be 1, 0, 0. And then we'd have 1, 0, 1 and so forth. So we just go all the way down, kind of swapping those values out. Until we get all the possibilities, right? And the way that we can see what the number of rows would be is we look at the total number of inputs, which in our case is 3. 2 raised to the third power is a total of 8 rows. So that's 8 outputs. So that's the number of outputs we're going to have. So let's just think through a few of these, right? A and B, if A and B are A and B, right? A and B, 0, 0, 0 and 0 gives us a 0. So this is going to give us a 0. I'm looking at the first row here. 0 and a 0 ANDed together is going to be a 0. And if we OR that 0 with another 0, which is the value of C in this first row here, then 0 or 0 is also going to be 0. And then we're taking that and we're knotting the whole thing, right? So we knot 0. So the opposite of the 0 would be the 1. And so our value right there is going to be 1. All right, let's do another one. Let's do our next row here. 0s and 0, A and B, we're zeroing. We start with the innermost parentheses. So we have a 0 and a 0, right? I'm now looking at column number 2. I'm sorry, row number 2. A 0 and a 0, that's going to give us an outcome of 0. And then we're going to OR that with another 0 because our value of C, I'm sorry, not 0, with a 1 because our value of C in this particular row is 1. So 0 or 1 is going to be 1, right? Because if either of them are true, then the final outcome is true when you're using OR. And then we have to knot that. So knot 1 is going to give us a final value of 0. Okay? And so if you go through here, you'll see that it's 1, 0, 1, 0, 1, and then as it turns out, the rest of them are zeros. So what I'd like you to do is sort of go through this diagram and just make sure you can fill out this truth table. It should be in the book, and you can just check your answers and make sure it matches what's in the book. All right, so that's it for today. What I want you to do, I want you to plan next week to have a quiz over some of these concepts, right? And at the beginning of class. So make sure that you read the rest of the chapter and pay attention to your vocabulary words. At the very end of the chapter is a section that's all about the important vocabulary words that we had in that section. So make sure that you understand those as well. That you get these concepts of working with binary numbers, converting from one to the other, and this idea of working with these operations of and, or, not, and XOR. Okay, and as always, let me know if you have any questions. No assignment specifically this week other than to read it and understand it and be prepared for the quiz next week. All right, have a good day. I'll talk to you later.